Probability is all about trying to know what's going to happen. We use laws and formulas to try to calculate the odds of our success. However, there are these times where we simply can't know what's going to happen, and even worse, sometimes thinking we know can actually cause us to know less. My name is Ariel, and today we're talking about what happens when we mix probability with game theory. So, what are we doing today? Well, as 109 students, we have this choice we have to make between studying for the final or doing the challenge. So what we're trying to do is solve that based on the average score we're expected to get out of each choice, modeled as a function of the hours we put into them. So we can start with modeling the grades of the final exam as a function of hours. You can check the project documentation to see how we did this with MLE estimates and something like that, but it's basically just the normal, super boring. Here you can see I'm just moving the hours, the mean shifts towards the right, and the variance gets smaller. Big surprise, you study more, you get better grades. Who could have seen that coming? Yada, 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 super boring. Let's move on to something more interesting. Now the challenge is where it really starts to heat up, because unlike the final, we just don't care about how we do, we also care about how the others do. It's not the same if it's just everyone participating, putting in a lot of effort, than it's if it's just a small proportion of the class who just don't care about it that much. Now, we know that about 10 people will participate in this challenge, so without assuming anything, our prior odds of winning are 10%. Everyone is equally likely. However, we can do some research and some simulation, the specifics of which we'll get to later, to get a distribution of how a winner would spend their time and compare it to a background distribution of how the class as a whole spends their time. With that, we can get everything we need to plug into Bayes' theorem and update our beliefs. So here we have the code for doing just that. We can see we have the distribution of our classes hours we got from our survey and the winners distribution, which again, we'll get to in the project documentation. Here are our constants. We see how many people we expect to participate in the challenge based on class size and historical ratios. And you can see the code down below that implements a Bayes formula for each choice of hours we make. And if you run the code, you can see that our best option is going for 17.5 hours, where we update our chance to 22%, twice as much as before. So now we're one step ahead of the competition. Now this one step ahead has a technical term, it's called K-level. At K-level 1, we are one step ahead of the people at K-level 0, which means they're not thinking their strategy through. We, however, know how they will play and can therefore plan better and beat them. And as it turns out, people don't like to be one-up, and there's no reason to believe they will not react to our reaction, so why not bring everyone else to K-level 1 to see what will happen? To do this, we need to do two things. First is defining this utility function to see how people prefer extra chance in winning against the hours it takes to get there, the specifics of which don't really matter. But the most important thing is this softmath function, which is a sort of sigmoid function, but extended, and basically means we're updating the reaction of people based on this perceived utility. And this beta parameter over here basically means how sensitive each agent is to the utility. Is beta of 0 means the utility doesn't matter and their behavior is random, but as beta grows to infinity, the weight of that utility means more and more to them. So we can run our simulation, update the distribution of the class's hours, simulate new winners, and what do we see here? Turns out when everyone does our perfect strategy, it's not so good anymore. And get ready to see what happens when we keep trying to anticipate the other player's move. Now, if we set a very high beta, we have very smart players, and go all the way to 10 rounds to see what happened, we see that a clear winning strategy emerges. 2.5 hours, this is mostly arbitrary, but let's say that's the winning strategy, and everyone being so rational bunches and goes to that strategy because it's the best one, then whatever way we sample our winners doesn't matter, all the winners are going to come from that category. So for the next round, everyone wants to stay in that category, and for the next, and for the next, and for the next, we have reached a stable point. This is called the Nash equilibrium, and notice that our chances are 10%. Everyone is doing the same thing and is therefore equally likely to win. And notice that the shape of the Nash equilibrium has to do with the other parameters, how we sample our winners, the cost, but we will always get a Nash equilibrium using a very high beta. Now, if we give our players a lower beta, everyone is not going to go to the winning strategy at first. Some of them will go a little bit above or below, but since they are not oversaturating the winning strategy, they will have the better chance of winning. So for the next generation, everyone moves towards what they are doing, except a few that try something different, which that becomes the winning strategy, and so on and so forth. We start looping around. The shape of this loop, the period, the winning strategies depends again on how we sample our winners, but if we have a lower beta, we are guaranteed to see this situation. And as it turns out, it has been proven that for every complex system like this, we will always either see one of these two things. We either get a Nash equilibrium with equal odds of 10%, or we get a looping pattern where we really never know what the R is going to do because we keep updating to infinity. So our odds here are still no better than random, 10%. So in the end, John Nash has stabbed us in the back, and we never really know what's going to happen, no matter how hard we try, no matter how we sample our winners or how we model utility, we still get 10% chances of winning. So, are we doomed? Is this the end of probabilistic models? Of course not. Inference has a great role in explaining why this kind of patterns happen all over the place. We now only need to accept that what we think may change what happens.